All right, hey guys. So I'm going to talk about self-organized criticality and visual processing. I'm going to primarily focus on this paper, which is Adaptation to Sensory Input and how that tunes visual cortex to criticality. But then I also want to make some comments just generally on the computational advantages of criticality during visual processing. So why does it happen? What's the functionality of it? So just some quick background on criticality. Criticality characterizes an archetypal phase transition that's found in many, many dynamic systems in nature. So if we adjust one control parameter of the dynamic system, we can move from one stable phase to another. And one of the key features is that at criticality, which is this point here, right in between the phases, effects of fluctuations or noise or input, however you want to call it, are scale-free. So below criticality, which is seen in red here, if we introduce some noise, we can see that the effects of noise are quickly damped. In other words, the system stays at its stable state down here. Above criticality, let's say the system is in this state up here, we introduce noise, and again, the effects are quickly damped, so we stay at this stable state. However, at criticality, the effects of fluctuations take longer to be damped, and so you see noisy effects inside the system. These effects of fluctuations are power law distributed, which means that they occur at very small scales and then also at very large scales. You can map the shape of fluctuations at one scale to the shape of fluctuations at any other scale. All right, so an example of criticality in the brain is neuronal avalanches. So let's say our critical system is a densely connected neuronal network. And our control parameter is the average synaptic strength, which translates to one neuron's probability of firing after a presynaptic spike. So if this probability is very low, below criticality, and we introduce some perturbation, in other words, we cause this many neurons to fire, we see that there's essentially no propagation, right? And then above criticality, above the critical point, some perturbation, actually just to one neuron, leads to this explosive growth. But at criticality, we perturb the system and we get these avalanches. And avalanches map well to perturbations, so different avalanches for different kinds of perturbation to the system. And they're also scale-free, so the avalanches can occur in very small sizes and then also very large sizes. So in 2015, this group knew that neuronal avalanches occur in the visual cortex. But the thing is that strong input, we know strong input drives this should be a densely connected recurrent network away from criticality. So on the left here, if you parameterize coupling weights using max eigenvalue of the matrix describing synaptic weights, increasing that beyond 1 goes into the supercritical stage, and below 1 we're in the subcritical stage. So this is again just showing you that criticality is controlled by synaptic strength, but the same phase transitions showing criticality can be controlled by your rate of input. So if you increase input spikes per time step, you also get this phase transition showing criticality. So if we have too much input or too high a rate of input, then we'll be driven away from criticality into this supercritical region. So on the onset of visual input to the visual cortex, the visual cortex is driven away from criticality because you can kind of consider the onset as a strong input immediately. but it nevertheless tunes itself back to criticality for the rest of the duration of stimulus. So if you kind of open your eyes, your visual cortex might be driven away from criticality, but then as you continue looking, the cortex tunes itself back to criticality for the rest of the time that your eyes are open. So we have this question now: how does the self-organized criticality actually emerge? Because we think it's a property of the network itself, which means it is self-organized. And then I also want to talk about why it's computationally advantageous, which isn't covered in the study, but it's mentioned tangentially, and there are some surrounding papers on it. So just quickly, this study was published in Nature in 2015. It has over 190 citations, and it was done in the US at the University of Arkansas and Washington University. It's quite a nice study. So it's divided into two parts, where there's an experimental section and then they build a model to try and replicate the experimental results. In the first part, they're using multi-electrode array recordings that are stuck onto an unrolled visual cortex from these whole brains from turtles, actually. And they still have their eyes attached. And so what they do is that they drive retinal input using a movie. So you can see the movie is pointed at the retina, and that in turn drives input into the visual cortex, which is being recorded using this multi-electrode array. And then we want to count where avalanches are occurring, because we want to see what the distribution of these avalanches are. And so avalanches are included as temporally dense local field potential peaks. So whenever we get a peak in the local field potential, that's probably a number of spikes occurring together. And then if there's a dense number of those peaks, we think that's an avalanche. So we measure the onset time, the size, so that's just the number of peaks inside an avalanche, and then the duration of the avalanche, so when does it start up until when it ends. Okay, after they did that, they built the dynamic model, where I'll go into more details later, but this is a densely connected recurrent network of binary neurons, so they're either in non-firing or a firing state. 80% of these of the neurons are excitatory, and then 20% are inhibitory. And then every neuron inside that densely connected network has some input. So they call that the thalamocortical input. Now, they find a way to update the synaptic weights inside this model so that the experimental results are replicated. But we'll talk about that soon. And then they use this model to explain self-organized criticality. All right, so the results. They find, after observing the distributions of avalanches, that there are these two phases of avalanches. Initially, they call it the transient phase, where avalanches are not showing power law distributions in size and duration. And so you can see that down here, where if we count the avalanches just in this initial phase where the movie's turned on, they have this distribution. So you have lots and lots of small ones and then less and less larger ones, but then you get this bump down here of very large avalanches. And so this is a bimodal distribution. After the transient phase, the avalanches actually do follow a power law distribution, which is what you expect from criticality. So these avalanches are just after the transient phase, and they closely fit the expected power law probability density function, which is in the light gray region. And it's a region because it's where you expect the avalanche sizes to be given this many samples. So the power law functions are given down here. The probability of a certain size occurring depends on that size to some critical exponent tau. And then the probability of the duration also follows power law distribution, and it's given by the duration to some critical exponent alpha. And then this is kind of a nice picture showing you avalanche size on the y-axis. So these are very large avalanches, and you can see the duration graphed here because the x-axis is time. Okay. So initially, we kind of get some very, very large avalanches and many smaller avalanches. But then after that, we get avalanches perfectly following a power law distribution. So the fluctuations due to visual input are seen at every scale. They're seen at a very small scale and a very large scale, following a power law distribution, as you expect from criticality. Okay, but that's not all. So there's also a scale-free spatiotemporal correlation in the avalanche events. So now, if you map avalanche size and avalanche duration, you also get a power law relationship. And so this power law correlation in the spatiotemporal domain suggests that the avalanche distributions in the previous slide inside spatial domain and temporal domain are driven by this criticality here. And we can see that the critical exponents relating size and duration, that's beta, actually depends on the critical exponents of the duration distribution and the size distribution. So alpha came from up here with duration to critical value alpha, and then Dow came from up here with size to critical exponent Dow. So this is suggesting that, again, criticality in the spatiotemporal domain underlies the avalanche distributions that we observe. Okay. Now, let's look at the results from the model. So we essentially see the same thing. We see the hallmarks of criticality in these avalanche distributions emerging after an initial transient phase. So in the transient phase, again, we get a bimodal distribution in size and in duration. And so that kind of conceptually matches the experimental results, that we're also in the transient phase, we have a bimodal distribution and it's a non-power law fitting, and then it moves into a power law fitting. These results become empirically close to the experimental results with extreme subsampling, because a model will generate results at every single time step, but if you make some assumptions about how much time is actually in each time step, and then you subsample based on the frequency that a multi-electrode array actually records at, you can produce results that are really close to the experimental results. And in any case, like with doing subsampling or not, you see the hallmarks of criticality. So you see avalanche size, distribution following power law, as well as avalanche duration following a power law, and you see down here the scale-free spatiotemporal correlation is also seen in the model, regardless of how you subsample. Okay. The other thing to notice here is that in the model, what's happening because of the adaptation rule that they gave the model is that these synaptic weights are depressed during the transient, and you see this in this figure. So in the green line shows you synaptic weights from inputs, And then the black line is synaptic weights in the recurrent network. And both of them depress to this stable state. And then in the top figure, we see that input will be stepped up because that's stimulating the onset of visual stimulus, but the spiking rate of the recurrent neurons follows this bump and then attenuates, and so returns to this baseline spiking rate. Okay. So how much does this model actually explain? What can we get from the model? Well, it tells us that the self-organization mechanism that brings back the densely connected recurrent network to criticality is actually quite simple. And all we need to model is short-term depressive adaptation at synapses. So just very quickly, how that is actually modeled. In the first equation, what we're looking at is just how the state of a neuron is chosen at the next time step, and it's chosen based on this probability. And it adds together the incoming weight multiplied by the state of input neurons, plus a summed weight of all the connections from J to I at time step t, obviously multiplied by 1 or 0, whether or not the presynaptic neuron is actually firing or not at time step t. Okay, and then the updating rules are the same really for the synaptic weight matrix between neuron J and neuron I and the incoming synaptic weight vector. It's the same rule here. So we take what the weight was previously at that time step from neuron J to I, and then we add a recovery term and we subtract a depression term. So this recovery term is scaled down significantly. So this time scale here is like 200. And so it'll recover back towards the initial synaptic weights slowly, right? And then this is the depression term. And this time scale is fixed at around 20 compared to 200. So we depress a lot faster than we recover. And we depress by the previous weight if neuron J had fired. Okay, so that is modeling short-term depressive adaptation at synapses. So if a presynaptic neuron fires, then all the neurons it was connected to, those weights from that neuron will depress. Okay. Why does this actually work? Well, if we recall earlier, there were two control parameters to criticality. One was the average synaptic weight, and the other was the strength of input. We can see that in this figure. So at criticality, we not only need the synaptic weights to be at a particular value, we also need input to be at a particular value. So what this updating rule does is it brings down the rate of incoming input. It attenuates input so that the criticality due to synapses can emerge. Okay, so assuming synaptic weights are tuned, the network still needs a mechanism to attenuate the strong drive, and that overcomes the weakness of densely connected networks, densely connected recurrent networks. That weakness being that strong drive pushes it away from criticality. All right, so now that we know that the visual cortex is tuning to criticality during visual input, we should probably talk about why it's doing that. So what are the computational advantages of criticality? So there's an increased dynamic range or susceptibility to input. So that is the vast combinatorial space of input maps to a really big possible space of output, in this case avalanches. Instead of, if you imagine from earlier, again, various inputs occurring and then the output always just being a steady state, right? We see these avalanches which are mapping the combinatorial space of inputs. So that kind of implies itself that a wider range of computation is possible. And then we can also make a similar argument to say that information capacity of the recurrent network is maximized at criticality. So if there's a larger possible range of pattern activation inside the network, then it has higher entropy and a larger possible number of states it can occupy, and therefore larger information capacity. Furthermore, we also have observed experimentally and theoretically that the fidelity of information transmission is maximized at criticality. So you can measure the mutual information between input and then output states, and that mutual information tends to be maximized near criticality. So let's say sensory systems kind of have these recurrent networks which are constantly activating and they represent what's happening out in the world. Then if those representations wanted to be very accurate to what's happening out there in the world, then the network should exist at criticality. So the representations can occur at criticality. There was also this really nice result I found here where training a recurrent neural network by maximizing mutual information between output states and input actually placed the spiking recurrent neural network at criticality. So that's another example where criticality emerges without external control, just by using an objective function that maximized mutual information. Okay, so I just wanted to conclude by talking about like the beauty of all this, of criticality in visual processing. So I think this captures one of nature's stunning abilities to engineer computation inside the spatial temporal domain. So even though inputs are like continuous and encoding needs to be continuous in the spatial temporal domain, we still managed to get like very precise computation. And it also points to hallucinatory or representational theories of visual processing, which I kind of just alluded to, where we have these sensory systems that are persistently firing and then they're perturbed. So they receive some kind of fluctuation or input or noise from the environment, and that leads to the fluctuation having a large effect on the system, which changes our representation of what's happening out there. Yeah, that's all I wanted to talk about. Thanks.
All right, good. Thank you.